3 is a magic number. Yes, it is. It's a magic number. Somewhere in the ancient mystic trinity, you get 3 as a magic number. The past and the present and the future, faith and hope and charity, the heart and the brain and the body give you 3 as a magic number. It takes 3 legs to make a tripod or to make a table stand. It takes 3 wheels to make a vehicle called a tricycle. Every triangle has 3 corners, every triangle has 3 sides, no more, no less. You don't have to guess. When it's 3, you can see it's a magic number.
Hey there, Mr. Yansak here, and I will apologize ahead of time for what I'm about to put you through. We've got kind of a long lecture. This might be your longest lecture of the entire fall, so hate to do that to you, but the good news is it will be your only lecture for the entire week, leading you into your break. And so at least you got that. If you need to, don't be afraid to pause it every 10 minutes or between sections. What we're going to do is we're going to weave sections 4.3, 4.4, and 4.5 together as one kind of super lesson, because they all cover a common theme. And let's jump right into that common theme. Reviewing a really important idea from earlier. Congruent figures. What are congruent figures? 2 geometric figures that have the exact same size and shape. Check that out, right? We're talking about not just exactly the same shape, but also the same size. That's a huge differentiation between what you're going to talk about later in the semester when we talk about similarity. Now, to achieve that, we have to have our 2 figures with all congruent parts, corresponding parts, okay? Every single corresponding angle, every single corresponding side has to be the same. Now, what are corresponding parts exactly, corresponding sides and angles? Hey, that's another recent definition. Let's review that really quick. A pair of sides or angles that have the same relative position in 2 congruent figures. So I see a couple triangles here that they're telling us are congruent. Let's take a closer look. We can see that triangle ABC and FED are said to be congruent. That's what they're telling us right here. Okay, you can see the way that the notation looks. Be really observant of the order of the letters. That is huge. Notice that A is the first vertex in the first triangle and F is the first vertex in the second triangle. That's not an accident. What they're telling us when they point that out is that A here has to be the corresponding congruent angle to F here. Okay, those angles have to match up. Same thing with the second letters, B and E. Okay, the corresponding parts have to add up. I could go down to the 5th part, which is segment BC and ED. Those 2 sides have to be congruent. So you can see that 3 tick marks and 3 tick marks tells me that those have to match up. Here's the thing. Right? Here's the thing. Triangles have 3 sides and 3 angles. That's 6 total parts. This is a proof that you just walked through recently in a lecture, proving these 2 triangles were congruent once you had those definitions. And so they gave you a whole bunch of things. They gave you a couple sides that were congruent. They gave you some angles that were congruent. We came up with this middle side AC congruent to itself because, of course, of the, let me mark it for you, AC is congruent to itself. AC is congruent to segment AC because of the reflexive property, right? Reflexive property of congruence. And so look at that. All three sides are now said to be congruent. Two of them they gave us, one of them on our own. But then they gave us two angles that were congruent, right? So they really gave us four parts to start with. And then because of that nifty little theorem that you picked up earlier in this chapter, the third angles theorem, we knew that the last two angles, D and B, had to also be congruent. Look at that. All six parts are now outlined in this proof. And because of this, you were able to say, look, our triangles are congruent because of the definition of congruent figures. Yay, right? Well, that's a lot of pieces. That is a lot. And what we're going to look for today is maybe some way that we can prove triangles are congruent to each other without having to go through all six individual corresponding parts, because that is a lot of work. And so I've got a little something that you might be able to get from your teacher or pull off of Google Classroom. It's a little worksheet called The Myth of, be careful here, ASS, the myth of ASS. The pronunciation in this case is very, very important if you don't want to get in trouble. Okay, so this is exactly what we were just talking about, this argument that it brings us into. We're talking about congruent triangles, and for two figures to be congruent, you can see the outline part there, all corresponding parts must be congruent. Okay, so for triangles, as we just mentioned, that would be three sides and three angles. That's six pieces. The question here is, do we need those six pieces? Do we have to have all six of those pieces? Not necessarily. And so we're going to explore how many pieces we do need. Let's start at the beginning. Let's start with just one congruent piece. Is one angle enough to force two triangles to be congruent? Look at this. We've got two congruent angles. They're marked congruent, but look, they really are congruent. However, I think we would agree there's no way those two triangles are the same shape. So we're going to have to say no. What about just one side? Well, here's our one congruent side in each triangle, certainly a congruent equal length segment. But once again, those triangles are not even close to being the same shape, are they? And so one piece, I think we've just shown, is not enough. To which, perhaps, you would say drat, or double drat, perhaps even triple drat. I'll leave that up to you. How many drats that you would like to emphasize. Let's move on to two pieces, okay? Are two pieces enough? So there's three ways this could occur. It could occur with two angles, it could occur with two sides, or one of each. One of each would work, okay? Now the two angles one is kind of interesting because two angles really means three angles. You just did this theorem probably within the last couple days, right? If two angles in one triangle are congruent to two angles in another, then the remaining angles have to be congruent. The third angles theorem. Here's the problem. It doesn't give us any sides, and so congruent figures have to be the same shape and the same size. These triangles, without question, are the same shape. Look at that. In fact, if I did a what's called dilation. Look at that. Isn't that beautiful? We just made these into congruent triangles. However, that is not how they started. And so angles alone is never going to get the job done, unfortunately. Okay. What about the two sides? This one's a little tricky because when you first look at this, it doesn't look like they have two congruent sides. I mean, I don't think you would argue that the bottom piece is congruent to the bottom piece. Look at that, two tick marks. Okay, but it looks like this one going kind of up and to the left is way longer than the one kind of slanting down. But look at this, if I twist this around, I can show you without a shadow of a doubt that those are indeed really the same length. Okay, so two pieces, but then we go back to the question, are they congruent triangles? Are these two triangles the same shape? No, sorry, not going to happen. And then we have the one of each, right? One congruent angle, one congruent side. You can see the congruent angle down in the bottom right. Indeed, it is the same angle measure, and then the congruent side on the bottom. And yet those triangles are not the same shape, are they? And so 2 pieces is not enough. So this time you probably say something like, "Oh, but don't give up," okay? Because we're still way less than 6, and eventually we're going to find what we need, right? Let's try 3. 3 would come after 2, I believe. 3 pieces. Now it's going to get more complex because the combinations of 3 pieces are much more plentiful than with 2. First of all, we could have 3 sides. You could have side, 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 right? Where you have all 3 sides congruent to all 3 sides of another one. That's one way you could go about it. Or you could throw an angle in the mix and you could do 2 sides and 1 angle. But then you could do that 2 different ways because you could squeeze the angle between the 2 sides. That's called SAS, okay, because the A is between the 2 S's. Or you could put the angle outside of the 2 sides, which would then create an SSA or ASS. Excuse me. What if we had, instead of 2 sides, what if we had 2 angles? What if we had 2 angles and a side? This would be AAS because the side is not what's called the included side between the 2 angles. Boom. Now we have ASA. So there's another 2 combinations, AAS, which would be the same as SAA or ASA. And then finally, the one we haven't talked about yet, AAA. So in all, there are 6 different orders that this could occur in, 6 different combinations. We have to check them all out. I believe we should flip to the back side of your notes, or the second page of your notes, and examine 3 pieces. Here we go. Side, side, side. What do you think about these 2 triangles? Well, it sure looks like they're exactly the same. Now, just because I'm showing you one example is not a proof. This is not a proof by any means. But what I am trying to imply here is that I could try infinitely many times to create different triangles with the same 3 sides, and it would never, ever happen. It's impossible. This does produce congruent triangles. If I could come up with a counterexample, I would. In this case, I certainly could not. Okay, congruent triangles for side, side, side. What about side, angle, side? Now remember, this means the angle is between the 2 sides. It's called the included angle. The 2 sides basically make up the congruent angle in question. One of the trickier things about triangle congruency is making sure you read the parts correctly. Is the side between the angles? Is the angle between the sides or not? And so it will take a little practice to get that down. Please ask for help if you are not seeing things clearly. But the moral to this story is, look at that. What this implies is not that this happens for every possible triangle, because I can't draw every possible one, but what it implies is I could not find a counterexample. It means that as far as we know, it is guaranteed to produce congruent triangles for an SAS case. And so we're going to say yes here. What about the 2 sides in the angle where the angle is not between the 2 sides? So notice this time the angle is not tucked between the 2 sides. If it was SAS again, this would be the congruent angle marked right here, but it's not. So this is what makes the SSA or ASS. Anyway, they don't look the same, do they? Look at that. They are not the same. And so it looks like this one counterexample is enough to show that ASS is not going to guarantee triangle congruency. What about AS? So this time it's 2 angles and a side not between the 2 angles. Well, it looks to me like those are the same. Once again, not a proof, but what this is basically implying is I could not find a counterexample to prove it was not true. Now what about ASA? So this time the side is actually between the 2 given angles, the 2 congruent angles, okay? That's why it's different than AAS. They sure look congruent, and then if we compare them, they certainly are. Once again, not a proof, but could not find a counterexample. Because if I could find a counterexample, like for AAA, I would have given it to you. These are the same shape, no doubt about it, but they are not the same size. So this is the same thing we ran into with AA before. Because remember, AA really means AAA by the third angle theorem. Same shape is not enough for congruency. You know what same shape is enough for? Same shape is enough for something called similarity, which I'm sure you've heard of before and that you'll talk a lot more about later in the semester. If we enlarged it, we would get the exact same shape and same size, but the way that they're drawn, not so much, and so we have to say no. So it looks like, in conclusion, of the 6 combinations, 3 of them work perfectly and 2 of them do not work, okay? It's easier to remember 2 things than 4 things, and so the way I would put this is that ASS is really easy to remember. So don't make an ASS of yourself and try to use it. And AAA doesn't work because all angles ain't no good. You get it? You know, A. Okay. 3 was a magic number after all, wasn't it? 3 parts of congruent triangles is enough to give us, if it's in the right order, if it's the right parts, to give us congruent triangles. And that is the magic of this worksheet, is it kind of takes you through all 3 of the sections we're about to look at in a really quick little condensed version. Now we just have to go practice a little bit. Know these combinations. Remember, SAA and AAS are really the same, and ASS and SSA really are the same. It's the angle not between the sides, and one of them doesn't work and one of them does, right? Know the 2 combinations that don't work. That's really your job. These are officially postulates with a couple theorems mixed in. Postulates 19, 20 are SSS and SAS. 21 is ASA. AAS is interestingly a theorem. And if you want to fill these in, all you really have to do is say the same thing again and again. The triangles are congruent, the triangles are congruent, the triangles are congruent. You're going to see these same theorems coming up quite soon within the context of the main lesson. But those are the 4 good combinations. Now there is this one little bonus that we're going to talk about called the HL theorem. And we'll talk about that when we get there in just a couple minutes, all right? So let's move back to a regularly scheduled program. Postulate 19 is the side-side-side congruence postulate. Probably just wrote it down on your notes page, but you could also write it down on your theorem sheet. If 3 triangles in one triangle are congruent to 3, if 3 sides in one triangle are congruent to 3 sides in a second, then the 2 triangles must be congruent. Now remember, a postulate doesn't mean we actually have a proof for it. It means that we are accepting this to be a true fact, because no matter how many people would draw a triangle, you could have 1,000,000 people use the same 3 sides to make triangles, and all 1,000,000 triangles would be exactly the same. That's the way it works, just like on the worksheet. Okay. Let's put this into action, shall we? Look at example 1 here. We're now in your examples packet. What do you think about triangles DFG and HJK? Well, I see the bottom side, the left side, and the right side as corresponding congruent sides. So I am going to say absolutely that they are congruent. So I would say that this is a true statement. And when I say it's a true statement, the congruency statement is what we're saying, whether it or not it's true. This is true. And the reasoning is because of the side, congruence. I guess you could use the symbol, right? Postulate. That's a postulate, isn't it? All right. So one thing that's really good to kind of keep in mind is the order of the letters, right? Notice that D down here is the first letter that they use here. Notice what it is. It's between the 1 tick mark and 2 tick mark sides. Look at H. H is the first letter here. Notice how it's corresponding. 1 tick mark, 2 tick marks. They're in the same location. you do have to pay attention to the details, and the order of the letters are the details. I think in problem 2 we're going to have a problem because although we have matching 7s, and then 9 is a shared side, so 9 is going to match up with itself. 3 is not equal to 4, is it? And so you only had side, side. Side, side is not enough. So this one I would just say false, or not true, however you want to put it. What about the last one? Well, it looks like side, side, side again, doesn't it? So this is a true statement because of the side, side, side. Congruency postulate. All right. Let's take a look at a friend from the past, the distance formula, something you probably picked up in Algebra 1 and recently reviewed, the distance formula. Looks kind of like that, or if you're having a hard time seeing that, a little like that, right? It's the square root of the difference between the x's squared plus the difference between the y squared. It's really just a fancy way of writing the Pythagorean theorem. Most people remember the Pythagorean theorem from previous math classes. For right triangles, a squared plus b squared equals c squared. All we're doing is saying that, you know what? A is horizontal, so it's the difference between the x's, and B is a vertical segment, so it's just the distance between the y's. And so that's where that formula comes from. X minus x is like your a squared, y minus y is like your b, so y minus y squared. And that's where our distance formula comes from. Why do we need the distance formula for problems like this? Check this out, right? It gives us a whole bunch of points, whole bunch. And we're going to make a couple triangles out of them. And then we're going to try to see whether or not those triangles are congruent. Right now, the only way we know how to prove congruent triangles is side, side, side. So we're going to see the lengths of those sides. And that's where the distance formula comes in. I'm going to really quickly graph these points for you. Ba-boom! So there's J, K, and L, and whew, there's T, R, and S. Okay, and then of course we'll connect the dots. Boom! Look at that, 2 triangles, just like magic. All right. So are they congruent? Here's the good news about this. Notice that I have a couple vertical and a couple horizontal segments. Those you don't have to use the primary distance formula on. All right. You don't need that guy because it's just one-dimensional. All you really have to do is either subtract the x's, subtract the y's. The absolute value signs are just there to remind you that distance has to be positive. And so if I did for, say jk here, if I just did -3 minus 0 and got -3, +3 would be that distance. And you could find JL also by just subtracting the y values, or just counting, I guess, 1, 2, 3, 4, 5, boom, 6, okay? Now, KL, so that's this guy right here, you're going to have to plug into the distance formula. And so here's what that would look like. If you need to pause the video to really look at it, that's fine, but I just put the x's in and subtracted them, and the y's in and subtracted them. And so I got a 3 and a 6, and then I squared those. And 45 is not a perfect square. You are welcome to take the square root on your calculator and get an approximation, but you really don't need to. Let me show you. Because when I put the points in from this other triangle, TRS, I get the 3 and the 6, but look, I also get a root 45. So if you're just comparing numbers, you can just leave them as root 45s. Root 45 and root 45 are the same. You don't have to take the square root on your calculator and get something like, I don't know, 6.7 or 6.8 or whatever it would turn out to be. So look at that. 3 equal sides means 3 congruent sides. Equal side lengths is the definition of congruent segments. These are congruent triangles. These triangles are congruent because of side, side, side. So what we would say to finish this problem off is that we would say triangle, let's start at the right angle, right? So JLK is congruent to triangle, let's start at the right angle again, RTS, because or by the side, side, side congruency postulate. All right? These are longer problems because they require a little algebra, but don't be intimidated by them. They're not as bad as you think. You really just have to be organized. make a list of your sides and then find the distances and you'll be good. Here's a little proof, and I think it's listed as example 1 on your notes page. Mine has 3 steps, yours has 4, because my givens were both listed at the same time for step 1, so don't let that confuse you. So my step 2 here is actually going to be your step 3, and it's going to be a very common step. It's going to be called a shared segment step. LM is congruent to itself, LM. Okay, why are those segments congruent? Well, the reflexive property of congruence. The of congruence is kind of important because there's also a reflexive property of equality, so that's why you want to be thorough there. But the most important part is the reflexive property. So check this out. I've created a situation where I was given 2 congruent sides, and I have a third one now. And so because of the side-side-side congruency postulate, I have 2 congruent triangles. If you're gonna, here's the thing you always got to keep in mind on these proofs. If you're gonna use side-side-side, you better in your proof have the 3 sides ready to go. You can't say side-side-side if you haven't shown 3 sides. So if you can keep track of that, these proofs are going to be easy. The way they kind of did this up here is they did the same steps. Look at that reflexive property. So the segments are the same, and then side-side-side postulate. This is called a paragraph proof. They just wrote sentences instead of 2 columns. That's another way to do proofs. But we'll stick with 2 columns for our proofs, all right? No constructions, though, so celebrate that, right? We're not going to do any triangle constructing this semester. Hey, guess what? We're on into section 4.4, which will cover SAS and HL. If you need to take a break and just catch a breath, go get a snack. Maybe a cool drink of lemonade. This would be a great time to do it. But not me. I'm going to keep going. We're going to talk about SAS. This is an angle, and it's just made by 2 pencils. You could grab 2 pencils or 2 pens and do the same thing, right? The angle that you make is called the included angle. So that's why this is called SAS, because the angle is between the sides. When you put the angle between the sides, then you write it SAS. If it was not between the sides, you'd have to write either SSA or ASS, which I think we've laughed at enough, so probably that joke's getting old. Let's move on to postulate 20, which is the SAS congruency postulate. If 2 sides in the included angle of one triangle are congruent to 2 sides in the included angle of another triangle, then the 2 triangles are congruent. So once again, these 2 triangles have the angles between the sides that are congruent. That's 3 parts. They're in the right order. They are congruent triangles. Okay. Of course, we could do a little proof using this. Now, this is 4.4.4 example 1, or I'm sorry, section 4.4 example 1, and you have a little more information already open on yours. I think you have a couple givens. I think you have, oops, not that one. You have the angle BCA and DAC are congruent. Of course, on my copy of the PDF, it looks like the angle signs are D's, and the congruency sign is like an at, like at Gmail. So if your PDF is like mine, it kind of looks a little weird, but you have that, and then I think you have the final step, which is what we want to prove. So let's fill in what we need. Well, of course, the two given things, right? BC and DA was given to us, congruent segments, and then not only are those 2 segments congruent, but those 2 segments are also parallel. That's very interesting. Look at the little arrows that distinguish, parallel lines there. And then, of course, there's another one down here, right? So those tell us we have parallel lines. How is that going to help us? Well, let's think about it, okay? Why would this angle that they're telling us about BCA, that's this guy right here, right, be congruent to this guy down here, DAC? Well, this is where we have to use those parallel lines. If you extended those lines a little bit, and then extended that kind of line going across there a little bit, suddenly it looks like we have parallel lines and a transversal. It's kind of taking us back to chapter 3. And I'm pretty sure we would describe these two angles, this guy and this guy, right? I think we would describe those two angles as alternate interior angles. They're in between the parallel lines on opposite sides of the transversal alternate interior angles. Why is segment AC congruent to itself? Notice they called it AC and CA. That's just because when you name the triangles, you're kind of going in a different order, but it's still the same segment, AC and CA. Why is it congruent to itself? Once again, you use this a ton. The reflexive property of congruence. Think about looking in a mirror and seeing yourself, right? The reflection in the mirror. The reflexive property says that you are always going to be congruent to yourself, whether you're a segment or an angle, okay? Now, check this out. At the very beginning, they gave me the top and bottom segments. That's a side. And then we got alternate interior angles. We picked up an angle there, didn't we? And then finally, using the reflexive property, I picked up another side. Now, just because it says SAS in my proof here doesn't mean that it's SAS. We have to verify that if I look at the two sides, is the angle truly between those two sides? Yes, it is. See how those two sides make the angle? That's the included angle. That makes SAS congruence postulate. Congratulations, you've done another congruency proof. Let's not do constructions, okay? But let's talk about something that's not a theorem and not a postulate. It's called ASS. This did not work out on our little example sheet. And the reason it didn't work out is because in certain cases, you get something called an ambiguous triangle. You will not be tested on that term, but what it means is multiple possible triangles. I call it the hinge theorem. Notice that this time that included angle is not between the two sides, right? See how the angle's down here, but the two sides are up here, so the included angle would have been here, but those aren't congruent. So we have ASS here. That's a bummer, okay? Once again, just to make it really clear, look at the two sides. If we did have SAS, the angle would have to be up here to get the angle between the sides. It's not. It's down here. And so that gives us ASS. Okay. Here's why I call this the hinge theorem. The angle, or the vertex, I should say, where the two sides meet, I call that the hinge. And if I release that hinge, that side's going to swing down, and it's going to be too long for a while. See how it's too long? But eventually, see how it kind of comes back up? Check that out. And eventually, it hits the same side that we were on, leaving the same two sides in the same angle. Look at that. We just made that different triangle, that ambiguous triangle, okay? And so that's how that can happen. It doesn't always happen. Here's an example where I have two congruent sides in a congruent angle marked. This time the longer side's across here, it's way too long. It's not going to ever come back up and hit the line. There's no ambiguous triangle here, but we don't know that for sure. And so what SSA or ASS means is not that the triangles can't be congruent, it's just that we don't know for sure. So just remember ASS doesn't prove congruency. You don't have to know why. That was just a little bonus explanation. Now, here's a very special case of ASS. Check this out. For right triangles, which if you remember from your recent definitions are triangles with exactly one right angle. Oh, there it is. I see it. Okay. And the parts are called the legs. The legs are the sides that make up the right angle, right? And then the hypotenuse, of course, is the famous side that's opposite from or across from the right angle, okay? So what the HL theorem is going to tell us is that if I have two right triangles where one of the legs is congruent to one of the legs in the other triangle, and the hypotenuses of the two triangles are congruent, then I have, you guessed it, congruent triangles. Now, under normal circumstances, look what we would get. Two sides and an angle that's not between the two sides, that would be SAS, but at the end of one of the other sides. So that's ASS or SSA. Normally, that does not work. That does not create congruent triangles. But because of the right angle situation, it does. And if I brought this side over here and tried to like hinge it up, it would never meet that again. It would never create a separate triangle. It's impossible. And so you end up with this this case that always proves congruency because there's only one possible triangle. It's the right angle that does the trick. So if you get right angles, if you see a right triangle, right away think to yourself, ooh, I have one more option. Usually I only have 4 options, but in this case I have a 5th one because the right triangles have the HL theorem. So by the way, some people think it's really special because it only has 2 pieces, right? It's most of our there are SAS, SSS have 3 parts, and HL only has 2 parts. But what people forget is it only works for right triangles, and so the right angle is actually a 3rd part. It's really just a special case of ASS that does work. If you see that you have a right triangle and you notice the hypotenuses are congruent, if you can find one of the legs that's congruent, you know that you can use the HL theorem. Here is a little example, and what it's going to ask initially is that we redraw the triangles, okay? Notice how it says redraw these. What it wants us to do is it wants us to position them so they're kind of corresponding. Okay, so I'm going to put them like with a right angle like this so that they both look very similar to each other, all right? Now this one right here, the A is up here, the B is the right angle, and the C is kind of along here, and notice that the AC is marked. And then for this guy, the C is the right angle, the B is along the long side, and the hypotenuse is marked, and the B is up, or I'm sorry, the D is the short side up here. Okay, so that's what we have. Now the one other thing to keep in mind is that BC is part of both of these triangles. Notice that. So I can mark BC as a shared side. And suddenly what do we have? Well, we have a hypotenuse, we have a leg of a right triangle. And so that's why we can prove this by using the HL congruency. This one is a theorem. This one's actually one of the few theorems about congruency that we have, all right? Here is a proof that uses the same kind of premise, all right? This is example 3 in your 4.4 notes, and it gives you some information. It gives you a couple givens, and it gives you one of the given things is the perpendicular lines to write in. It tells you that you have a couple right angles. Once again, at least on my PDF copy, it might be my printer that's weird, but it didn't put angle symbols in. Like I have angle Z and angle Y. It has like a little D there. So I think that's just a symbol thing. But if yours is like mine, it doesn't look right. Number 4 has the triangles that are congruent. And number 6 tells us that what we want to prove. And so this is everything that probably was pre-filled out for you. And so we just have to fill in the blanks. Well, the only other given that we hadn't listed was the congruent segments. And I think we can start chipping away. The first thing that we do is probably break these triangles up like we did in the last one and write them separately, okay? Kind of like that. I call this, I have a kind of a nickname for this. I call this DST. DST. Draw, right? Separate, draw separate, and you guessed it, triangles. If you take your triangles and draw them instead of crisscrossing each other separately, it's a lot easier to kind of see what pieces should match up with which pieces. All that we did here is just label the pieces that let's take a closer look at them here, is label the pieces that they described to us in the proof. Okay, notice that they told us in the proof that WY and XZ were congruent, so those are labeled. And they told us in the proof that I had some perpendicular segments, WZ and ZY. Okay, and so that's why I have a right angle down here, and XY and ZY were congruent. That's why I have a right angle down here. Okay, now the one thing that they didn't give us is why do we have ZY and YZ? Why are those congruent? They gave us one congruent segment that looks like the hypotenuses they gave us, but they didn't give me why ZY was congruent to YZ. Well, think about it. ZY, YZ. That's right. It's a shared segment. It's the same segment in both triangles, because if you look in the figure, they both had the same bottom. And so that's really just a reflexive property. That was actually step 5, all right, that you're going to need to do. Why were Z and Y right angles? Well, that's the definition of perpendicular lines. Remember, they told us we had perpendicular lines, and that makes them right angles by the definition of a right angle, okay? All right angles are congruent to each other, and right triangles have right angles. So if you think about what we have now, we have hypotenuse leg, boom, you're done with this proof, okay? What could come next? These are probably the most common problems that you are going to see within this congruency stuff. They're called congruency statement problems. You'll like them better than the proofs because they don't go into as much detail. All right, you're basically just saying, are the triangles congruent or not, and why. You don't have to go through the whole proof part of it, but you still have to kind of figure out what's missing. Like in this case right here, I have 2 congruent sides given right off the bat, but that's not enough, is it? Oh, but wait, MO is a shared side, reflexive property. And so because of side, 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 the side, side, side congruency postulate, I could say these triangles are the same. Now be careful, because we have to go in corresponding order. For MPO, which started at M and went up to P and then down to O, right? We started between the 1 tick mark and 3 tick mark sides. Well, that would also be M on the bottom triangle. And then we would go to N to match up with P, and then we would end at O. You can't just write your letters in any order. They have to be written in corresponding order. It's such a minor detail some people don't think is important, but yet it is. What about this triangle right here, example 2? Well, we have a shared side again, and then we have another side and an angle. But unfortunately, this time, it's not the kind of a sequence that we like, okay? It's an angle and a side and a side. That's ASS or SSA. Now notice what the directions, well, the directions don't really tell you what to do on yours, but on the quizzes, there usually be something like this. If the triangles cannot be proven congruent, cross out the congruency statement because we can't make it. Just put a slash there. And then write CBD. CBD is short for cannot be determined. What you don't want to do is write CBD on this blank because somebody will think you're talking about triangle CBD. All right. And then the reason is just as simple as ASS doesn't prove congruency, right? ASS doesn't work. And so I think that's good enough for the answer. What about example 3 here? Well, they told us we have some perpendicular segments, GA and OT. Bam, right angle, right? Oh, except it's a right angle on both sides, so that's cool. And we have a shared segment. Now, with right triangles, sometimes you think of HL, but I don't know anything about GO and GT, the hypotenuses, but you don't need it because I've got 2 sides and an angle. Right angles are congruent to each other between the sides. That's SAS, my friends. And just to illuminate that a little bit more for you, I will fill that in. Here it goes. Side, angle, side. You see how the angles between the sides, right? And so now we just have to be careful that we name it in the right order. This one went T, A, G, and so we're going to go O, A, G to be in a corresponding order. Last one here, number 4. Looks very similar to the one we just had, except this time we don't have a perpendicular segment. Now they did give us a congruent angle, so this is like HV is an angle bisector, and we have a shared side. You have a lot of shared sides in these types of problems, so always keep an eye out. But unfortunately, this is angle, side, side. See how the angle's not between the sides this time? Bad news, right? Because ASS doesn't prove congruency. And so don't write a congruency statement. Just put a slash there, and then right next to it, just write CBD, cannot be determined. We don't know if they're congruent because ASS doesn't prove congruency. All right, good time to take a break, maybe grab a drink, or come back to it later on. We're going to talk about 4.5, and then we'll be done. 4.5 covers the last two of those conditions, ASA and AAS. And you can see here the little picture they have here. The side is between the two angles. Notice that if I take the side, both angles are built on that same side. That's how I know that it's ASA. The side is between the angles. And there is a postulate that tells me that ASA, two angles are congruent to two angles in another triangle, and the included side, then the triangles are congruent. So you can go ahead and fill that in if you want. And then right after that, very connected to it, is theorem 4.6, which tells us that even if the angles are the side is not between the two angles, even if it's AAS, it still works. You still get congruency, and that's a theorem. That's one of the only theorems in congruency. But these two are very closely related, and the reason why is because, as this proof shows, the third angles theorem. So this proof just says, hey, let's start with ASA. So, or I'm sorry, AAS. So we have two triangles up here that have AAS. And because of the third angles theorem, I know that those remaining angles also have to be congruent to each other. But then I have, right, angle, side, angle, which is a postulate which I can then use to prove the triangles are congruent. Another way of writing this is a cool flowchart way, but we're not going to teach you how to do that because we got our hands full just with two-column proofs, don't we? Same exact information if you want to pause the screen and kind of take a look at it. But there's just a lot of different ways of doing proofs, but we're going to stick with two columns. It's the most common. Here's some problems that you're going to see. Example 1 on your 4.5 examples, and you'll see they give us some triangles, and they say, hey, are these triangles congruent or not? So let's use our new theorems and kind of test them out. What do you think? Well, I do have vertical angles here. So this angle right here is congruent to this angle right here. Hey, look, angle, angle, side, super cool. Angle, angle, side, look at that. That is a theorem. That's the angle, angle, side theorem. So I would say yes on this one. This one has angle, angle, angle. Angle, angle, angle. I don't think that works, right? All angles ain't no good. So I'm thinking this one's a big no-go. What about this one? I have two angles, so there's angle, angle. Oh, but guess what? We got that shared side in the middle, the reflexive property of congruency. So I'm thinking that this one's a yes too because of angle, side, angle this time. Remember this one over here I think was angle, angle, side. Let's see how we did. The first one was yes because of angle, angle, side. The second one was no because angle, angle, angle doesn't prove congruency. And finally the last one was yes. They are congruent because of angle, side, angle. All right, we're awesome. All right, last 6 examples. Okay, finally winding down here. These are just some more congruency statements. Let's see what we got. We now have a full battery of help. SSS, SAS, ASA, AAS. Remember, AAS is the same as SAA. It doesn't matter which order you write it in. Either one's fine. If it's a right triangle, maybe even HL. But don't use ASS, which is the same as SSA. Those are bad. Or AAA. Don't use that either. What do we have here? Well, we got vertical angles. And that creates two angles and a side. The question, I think, is which one of these is it? Is the side between the angles or not? Well, it doesn't look like it. If the side was between the angles, it would be this one right here, wouldn't it? But it's not. So this is angle, angle, side. But that's okay. Angle, angle, side, congruency theorem. And we got to get the order right. Notice that R is the one angle I have not marked yet. So if I go into this other triangle, what's the only angle I don't have any markings on? V. Okay. And then they went to S for their second one, which is the single arc, the red one. So that would be U. And then they both end in the middle at T. Gotta put your letters in a corresponding order. That's definitely part of these problems. And sometimes people do really good with the SSS part, but struggle with the order of the letters. All right, what do we got here for number 2? Well, it looks like we have vertical angles again. They're throwing a lot of vertical angles at us today. Here's an angle that's congruent to an angle right here. And so that creates angle, side, angle, right? Because the right angles are congruent. So angle, side, angle, congruency, postulate. And we got to get the order right. A is the right angle, D is the right angle, B was down to the short side, so the short side here would be E, and then C. Boom, very nice. This one's a little tricky just because they twisted the top one, they rotated it a little bit different. It also looks like the angle that's given is not between the two sides. So a lot of people are going to freak out and say ASS can't be done. ASS, no way. But remember, we don't just have ASS, we have a leg and a hypotenuse. And so I think it will work. Right angles, right triangles with legs and hypotenuses allow us to use the HL congruency theorem. And we just have to get the order right now. They did F first, which was at the end of the double mark side. Here's the double mark side. I think that would be H. Then they went to G, which was the right angle in the middle. Our right angle would be J. And so that means we would have to end with K. That's the only letter left. Okay. All right. Why don't you try 4, 5, and 6 now? You give them a shot. Okay. Go ahead and pause. Try 4, 5, and 6. And then we'll come back together and see how you do. Hey, welcome back. You weren't gone very long. Let's see what you did. Did you on this one? Did you find the shared side here? Because if you noticed, MP was congruent to itself because it's a shared side. You notice that we have ASA, which makes us very happy, doesn't it? ASA is a congruency postulate, and so they did LMP, and so we're going to do NMP to be in a corresponding order. NMP. These letters have to be in that order, otherwise it's an incorrect problem. Here I have some vertical angles. Did you find the vertical angles here? Okay, what did that give us? Angle, angle, side? Yeah, angle, angle, side. Right on. So angle, angle, side is a congruency theorem. And EFG went from the right angle to the non-vertical angle. So we're going to go from the right angle down here, H, to the non-vertical angle, D, and then back up to the middle to end at G to get in the corresponding order. If you got that one right, give yourself a star with a hat. A little ball cap on there. Nice job. Number 6. Some people are going to get stuck on this one because they might see the vertical angles in the middle, but then they'll be like, well, all I have is a side and an angle. That's not enough. 2 pieces is never enough. But never forget parallel lines. If you have parallel lines, you're going to get alternate interior angles here and here. You're also going to get alternate interior angles here and here. If you extend the lines and draw the transversals, it's easier to see it. So don't be afraid to do that if you need to. Take out your straight edge and run a line, through here and extend those lines and take a look at those transversals, and maybe you'll see those better. So the cool thing is I have I have congruent triangles. ABD went from my blue angle to my purple to my green. So I have to follow that order. So I'm going to go from E to B to C. So EBC, corresponding parts. And then here's the kind of cool thing. Depending on what you use, you have a couple different options. If I use like these three pieces right here, it would be angle, side, angle with the side between the angles. Okay, that's a postulate. But if I used, say these three pieces right here, this piece and this piece and this piece, now the angles are not around the side. The side's not between the angles. And so this is actually one that has multiple right answers depending on what pieces you use. You could have definitely used angle, angle, side. Also, that one is the one, other than HL, that's the only theorem. But anyway, holy cow, you guys made it. Sorry for how long this was, but that's it for the week. Remember your reference sheet. Remember, more importantly than anything, the four good ones. ASS, don't make an ASS of yourself, right? And AAA, no, all angles ain't good. So if you remember the two bad ones, just remember everything else works. And these are the ways to prove congruency. I mean, there is the one other way, the +1, right? To prove all the pieces are congruent using the definition of congruent figures. But who would want to do that? Stick with the shortcuts. You got 4 main ones plus the special bonus one for right triangles HL. And you'll be getting used to these over the next assignments. And when I say the next assignments, this is not going to make you very happy, but we covered 4-3, right? And we covered 4-4, and we even covered 4-5. So the bad news is you're now going to have these 3 assignments, but the good news is that's all you're doing all week long. That's all you're doing Monday, Tuesday, Wednesday, and then if you're not done, you have a 4-day weekend to finish up, and that's it. So 1 long video, 3 assignments. I know that you may be freaking out right now, but you can do it. I know you can. So go get them, Tigers, or something like that. Hope you have a good break.
Particle man, doing the things a particle can. What's he like? It's not important. Particle man, is he a dot or is he a speck? When he's underwater, does he get wet? Or does the water get him instead? Nobody knows. Particle man.